Well, good afternoon. If you're not falling asleep right now, you will in 20 minutes, so. So, let's crack on then. Where should we start? This is a story of West Coast Grid, West Coast Mainline in Handsacre Junction. So it's more or less a story of what did we do to integrate the designs into grids. And there are some prerequisites there. HS2 route joins West Coast Mainline in Handsacre, and further they need to continue on the conventional route north. HS2 design is mandated in HS2 snake grid. West Coast Mainline is an absolute track geometry, obviously, so is mandated in West Coast grid where the assets sits. HS2 snake grid is well defined. West Coast grid is a legacy grid with no formal definition. So we have an issue there. That means we need a workable transformation for the digital world we live in. A few things about HS2, as you guys know, the elephant in the room, obviously, is the obvious, the largest infrastructure project in Europe. Goes from London to Manchester and Birmingham when finished. Phase 1 delivery 2029-2033. It will integrate with conventional railway network and new terminal stations and a few more facts as well. There we go. Okay. I'm not going to tell you too many things about West Coast Mainline. You guys know probably more than I do. I will ever do. However, a few dates to consider: 1838, 181 kilometers. 31 years later, 1,127 kilometers. Connections to Northampton, Birmingham, Manchester, Liverpool, and Edinburgh. Modernized absolute track geometry implemented 1994-2009, 125 miles per hour, or 200 kilometers per hour. So it's one of the busiest routes in Europe. So what is the issue? Well, the project required a transformation in such a way that the alteration to the West Coast Mainline infrastructure are seamlessly and accurately linked with the respective high-speed 2 works. So across that dotted boundary, you can see that we have the West Coast Mainline, which we do have the assets maintained in West Coast Grid. ATG is maintained in West Coast Grid. West Coast Grid is installed in situ. What does it mean? We have spigots on the oily boundaries and super PGMs precisely marked and coordinated. There is no formal definition of parameters, mathematical formal definition of parameters currently. And by not having that, there is no GNSS compatibility. Then we have the HS2 mandated design in HS2 survey grid. HS2 is not in situ, so it's not installed right now. There is a formal definition and is GNSS compatible. That poses an issue for us, and that again caused us to inquire ourselves and see how we can work it out. So that means we need to have a workable transformation in such a way that the alterations to West Coast Mainline infrastructure works are seamlessly and accurately linked with the high-speed 2 works. So the proposed solution: we sat a little bit, looked at it. Obviously, we need to create a transformation parameter. That's the first step we'll look at it. However, we didn't go with that. We decided to apply a local projection, which is based on the transverse Mercator projection. However, a little bit more complicated. We went to a transverse Mercator with a fine pros process. Why was that? Because it's readily available across the design packages, across all the major design software suppliers. So what did we do? We've proposed, we had to do some surveys, right, obviously, where we've linked with the continuously observed reference stations, which are those three in the corners where it says the primaries on top left, primaries GNSS, and then we've installed five primaries. We installed 7 secondary coordinates, seven secondary PGMs. We did traversing, we did leveling, and also, as you could see there in West Coast, in the middle West Coast grid, we had already the existing spigots portrayed here, which we had to coordinate as well in the same survey in order to obtain 2 sets of coordinates in both grids. And for that, we would have obtained the transformation parameters. So the work was undertaken to be compliant with the network rail standards. It was finished, it took a period of 3 months and finished around March, I'm lying here, May 2021. And a further secondary benefit was to provide the survey control suitable for the construction phase of the project. And we did a GNSS campaign with all that in place over there, 5-step processing. We verified the ordnance survey core stations. We validated the observations, checked internal and external observations. We did post-processing, primaries to cores, those ones 1, 2, 3, and then there's a little one in there, Litchfield in the middle, 4. And then we did post-processing on the secondaries in relation to the primaries, as best practice says, and as in relation to network rail standards. Right. Then, obviously, we had to do traversing and leveling to, excuse me, to observe those those 104 spigots and existing markers from the West Coast Mainline. And also, we processed them in HS2 survey grid at the same time. So there are 9 steps over there, where we processed in various ways by trying to get the best fit plane first, and then we calculated the elevations for the main traverse. We did the integrity checks observations for the trigonometric observations. We tested the traverses. We constrained the traverse, and then we calculated the HS2 snake grid coordinates. In West Coast grid, it was the other way around. Excuse me. In West Coast grid, we had the coordinates given, 100 and, what did I say there? 4. We'll see them in the next slides. So we checked the observations against the supplied coordinates. We did fix the leveling on the West Coast grid height on the local plane, and then we've did the leveling and trigonometric processing by updating the West Coast grid coordinates and excluding the outliers, as we normally do every service. Excuse me, I think I need some water. Just leave you with this beautiful slide, which is not really explaining, but I usually live on Teams, so if I behave like a sociopath, let me know. So what's happening there? The de facto standard method for conversion of data between two projected grid systems is to derive and implement a Helmut transformation, which is coordinate, shift, rotate, and scale. That means that such transformations, if we have multiple grids as we have them in Handsacre, you need multiple Helmut transformations. or create a vehicle, a grid vehicle, to transform from one projected grid to another by using another grid. So this process can be laborious and error-prone, so particularly when manual entry of parameters is required. So instead, we went to transverse Mercator with a fine pros process, which is a subclass of transverse Mercator, which includes a final processing step that is following the projection of the geodetic latitude, longitude onto the transverse Mercator plane, then applying an affine transformation to the gridded coordinates. We're getting there. So this is another beautiful slide. We had, using the acquired 2 data sets of control points, the affine parameters have been calculated via the process described, which is 3 steps again. We had to define the transverse Mercator projection in the area. Then we added a affine transformation with those beautiful matrices over there. And then we estimated the A0, A1, A2, and B0 via least squares. Thanks to Jim, the main author of this study. Right, so these are the results. So pre-fit, so initially, as you can see, the results of parameterization over there. On the left-hand side of the left table, we have the pre-fit results, which is outrageous, standard deviation of 5 meters and 4 meters. Anyway, once we've applied the post-fit, once we've applied the affine transformation, the affine parameters, we got to a standard deviation of 4 millimeters on eastings and 3 millimeters on northings, with a maximum and minimum 8 plus 8 minus 14 on eastings. I think those are the worst ones, yes. And the results are shown in the right-hand side table. However, we couldn't get away with it, so we had to apply a Helmholtz transformation in the end. So that was our check. We did a Helmholtz transformation, and the residuals were quasi identical. As you can see them, 0.4, 4 millimeters on eastings and plus minus 3 millimeters on northings on the bottom. And 101 points, I did say I'll mention them, 101 points out of 104, 3 were removed due to mistakes, gross errors, and outliers from the survey. Okay, so we defined the projection. What's next? Next, we have to make sure that the projection is suitable for the digital environment we're working on. So because West Coast Grid is a legacy grid, featuring relatively unknown characteristics, this necessitated an assurance check on the fitness of purpose. And to check that, we've downloaded a coarse digital terrain model sourced from Shuttle Radar Topography mission, and we've used it to generate ellipsoidal reference ground points across the domain of interest, Bowen, or the junction. These values enable the generation of a heat map showing the map projection distortion characteristics of the new projection for the area of interface. So all distortions were within 20 ppm. Those West Coast grid at Handsacre is confirmed as viable. So not a really big surprise, but we were expecting something similar. And that means it's viable for design and engineering coordinate space, as we hoped for. It should be noted also that the parameters denoted only operate to attain planar grid coordinates and do not affect or indeed achieve heights above project datum. And as part of the control survey works, we've determined that there is a 69 millimeter difference in levels between West Coast grid height and HS2 survey grid, or HS2 survey reference frame, vertical frame, which is over there. So by applying those 69 millimeters, we got a trend line for each point from low miles to high miles. And as you can see, the trend line, the red one, which is referring to West Coast grid heights, is within 1 millimeter, plus minus, as when we apply the correction. Implementation. So the West Coast TMAF file was disseminated to users to Bentley Managed Workspace. What is that? If you're not a surveyor or a designer, you don't know what that is. So Bentley Managed Workspace, practically we've created a little file, a parameter file, we've applied it and distributed formally to projects around the area. We've put it into the common data environment and created a little guidance where each designer can apply, yes, or include this file into the design software. And in this case was Bentley MicroStation. And there are a few benefits. It's reversible, increasing efficiencies, compatibility with web map services. I'll show you another slide at the end where I'm showing the web map services. You can, is the assignation of coordinate systems, geographic coordinate systems made within the design data, so you can easily identify what grid is your file in, obviously. We kind of have this issue in Network Web. And so on, direct relationship to West Coast grid and GNSS positioning and so on. However, we've learned some lessons as well. So HS2 remitted Network Rail through our NetworkWorks contract to develop the Handsacre slow line connection in parallel with HS2 main works. Civil contractor are remitted for the design of railway substructure elements such as civils, embankments, viaducts, and structures. Those ones were blue. These figures outline the contract delivery partition mechanism employed by the contractor entities, thus highlighting the necessity for a robust and efficient transformation approach for design information between the two grid systems to enable track alignment developed by all NetworkWorks to be used by the main works civils contractor to define railway substructure. And the lesson we've learned here is that when we're reprojecting an arc of radius of 1900 meters, 1,900 meters, in process of translating the curved track alignment geometry between survey grids, it unavoidably fragments the true design geometry, as shown in this slide. On the top left, we have the properties of the arc in the HS2 survey grid. On the bottom right, we have the properties of the arc when reprojected to West Coast grid. As we can see, we have it does say there that it's an arc, here it's a line string. So what this mean is the geometric arc was broken down into 64 linear chords, losing its true geometric properties. So as linear straights are geometrically preserved when transformed between survey grids, selecting the interface point on a straight with a fixed gradient mitigates this inaccuracy. So it is the recommendation that when there is a need to design and deliver track work across different survey reference frames, project scope and contract boundaries are defined with consideration to the track geometry features to ensure that there is a section of straight with constant gradient. So this is Brian's bit. I'll continue reading it. The alignment interface reference chainage. So from both West Coast Mainline and HS2 use an absolute reference chainage to provide fixed linear positioning of assets along the route. These are defined from independent datum points and follow their respective corridors as such as do not feature commonality between the systems. In line with network requirements, the Network Works contractor has used the West Coast Mainline ATG chainage to define the start stationing for the alignment model. Therefore, the proposed alignment interface location can also be referenced as a linear position in both systems, as shown over there. Although the use of chainage to describe linear location of design boundaries is commonplace, due to the differences between datums and track baseline lengths, there is a need to manage the interface in coordinate space. Furthermore, the definition of a single point will ensure commonality of the alignment at that point. And this is the same point in two survey grids. As you can see, you have two different coordinates. And yeah. So the validity of the West Coast Grid transverse Mercator with defined process in relation to the design interface is that although this paper recommends validity of the TMAF only within 500 meters, 500 meters mean those circles over there, the points in this line can be seen that the identified design interface point, location of the CRD defined interface on the straight line, is beyond this boundary. However, the TMAF heat map from a previous slide, from my presentation, is slide 14, but I can see that this is 244, so it could be slide 232 probably, demonstrates within this zone that the coordinate space remains of an engineering quality. That's very important and can be utilized to define the alignment geometry in both survey reference frames. So the conclusions, the TMAF can be used as a flexible solution, can be used, the principal application is, it's not only for railway, it could be used for every single legacy, every single project where we're interfacing with the legacy grids or legacy asset grids, where we can replicate that. In particular, the principal application is, again, to define local or legacy grids within the design software platforms. That's very important. It's accurate and compatible transformation procedure with infrastructure designs. Yes, significance of benefits, streamlining conversions procedures, reducing potential of errors, and there are a few other things. It's generic. That's very important. And this is the example I was mentioning about. I'll pretend that I have a pointer here. This is a snapshot from a general model, a general design. This is MicroStation, right? We have the base model is in, as you can see, the current geographic coordinate system in the little window is TMAF West Coast Handsacre, with the properties on the right of the projection. We've referenced a series of models from two other coordinate grids. One is the HS2 snake grid, and the other one is Ordner survey. And these are referenced into the model with survey accuracy. It's more than what we need. Okay, so I think that concludes the presentation from my end. If you have any questions, obviously after the next one.